Am I audible? Am I audible? Hello? Okay. Is it fine now?
I'm getting some noise. Anyone getting?
Is it fine now?
Now it's clear, sir. Now it's clear.
So hello everyone. This week we are going to discuss about force and the movement in the beam. And before that we will be talking little bit about center of mass and centroids. Because this concept will be very helpful to find the forces and movement in the beams. Or there are various kinds of beam and different kinds of force act on the beam. For example, let's say I have a simply supported beam and there might be a uniform force which is acting, or there might be a force which look like this, which varies with the horizontal distance x. And in order to find the forces, these kinds of forces, first we need to see what is actually centroid, and we need to know how to calculate the centroid and center of mass and so on. Then we can actually calculate the resultant force which is acting at some specific point. And then we can do our usual practice which we are doing since last 2 weeks, the force balance and movement balance, to calculate the required things. So just to recap, so in order to find the center of gravity, the location of the center of gravity, we need to actually use the moment principle, which says that resultant moment is equal to sum of moment from all particles in body. So basically I have a body and it has some location. Let's say this location specifies the center of gravity, and it will have some movement. This is the weight of the body and this is the location of center of gravity, and it will create some movement, and that movement is actually x bar w, and x bar is the location from the origin to the center of gravity point. Now this movement will be equal to sum of all movement which is due to the particle. So each particle inside this body have weights. So each particle have their own weight. These are very small elemental particles and it will have their own weights, and therefore each particle will create a movement, and it is equal, the resultant movement will equal to summation of all these movement, which can be written by x w, and we have to integrate it, so it's dw and then the integration sign. So the location of the center of gravity will be x dw, by
by
W.
W.
So this
So
is
this is
the
the
X
X
location,
location,
and
and
similarly we
similarly we
can
can
find
find
Y
Y
location
location
as well
as well
as
as
Z
Z
location.
location.
And in the
And in the
same
same
manner,
manner,
the
the
location of a
location of a
center of
center of
mass can
mass
be
can be
given
given
as
as
by
by
this
this
formula.
formula.
And so
And so
on.
on.
And
And
the
the
centroid
centroid
can be
can be
given
given
as
as
so this
so
is
this is
again
again
the
the
vector
vector
version of
version of
the
the
center of
center of
mass,
mass,
and the
and the
centroid
centroid
is
is
so this
so
is
this
the
is the
centroid
centroid
of
of a
a line
line
element.
element.
It can
It can
be
be
given in
given in
terms of
terms of
area as
area
well,
as well,
and so
and so
on,
on,
or in
or in
terms of
terms of
volume.
volume.
So this
So
is
this is
centroid.
centroid.
This
This
is
is
location of
location of
center of
center of
mass,
mass,
and this
and
is
this
the
is the
location
location
of
of
center
center
of
of
gravity.
gravity.
Now you
Now you
can
can
see
see
that
that
these
these
locations
location
like
like
center of
center of
gravity,
gravity,
location
location
of
of
center of
center of
mass,
mass,
and
and
centroid,
centroid,
these are
these are
actually
actually
related to
related to
each
each
other.
other.
For
For
example,
example,
let's
let's
say
say
in the
in the
above
above
expression,
expression,
like
like
here,
here,
I
I
can
can
write
write
the
the
weight
weight
as,
as,
which
which
is
is
just a
just a
force,
force,
as
as
mg.
mg.
So
So
this
this
expression I
expression I
can
can
write
write
as
as
x
x
dg
dg
by
by
g,
g.
and I
And I
can
can,
so
so
here
here
I
I
keep the
keep the
mass.
mass,
Sorry.
sorry,
It
it
is
is
x
x
dm
dm
by
by
m.
m.
So
So
I
I
can
can
actually
actually
get the
get the
center of
center of
mass
mass
equation
equation
when I
when I
put
put
here
here
W
W
equals
equals
mg.
mg.
So
So
that is
that is
only
only
valid for
valid
the
for the
specific
specific
case
case
when
when
the
the
gravity is
gravity is
very
very
uniform.
uniform.
It is
It is
not
not
changing
changing
in the
the
direction.
direction.
Only in
Only in
that
that
case I
case I
can
can
get
get
the
the
center
center
of
of
mass
mass
relation
relation
from the
from the
center of
center of
gravity
gravity
relation.
relation.
And if
And
the
if the
gravity is
gravity is
not
not
uniform,
uniform,
then
then
this
this
expression will
expression will
become
become
this.
this.
So
So
this will
this
be
will be
now
now
center of
center of
gravity for
gravity
the
for the
non-uniform
non-uniform
case.
case.
And when
And
the
when the
gravity is
gravity is
uniform and
uniform and
parallel,
parallel,
then
then
it
it
will
will
reduce to
reduce to
the
the
center of
center of
mass
mass
expression.
expression.
And
And
similarly,
similarly,
one
one
can
can
reduce
reduce
to
to
centroid
centroid
from
from
center
center
of
of
mass.
mass.
So we
So
all
we
know
all know
that
that
mass
mass
can be
can be
written
written
as
as
density
density
multiplied by
multiplied by
volume.
volume.
So
So
from
from
this
this
relation, I
relation, I
will
will
get
get
x
x
rho
rho
dV
dV
integration
integration
divided
divided
by
by
rho
rho
volume.
volume.
So
So
now,
now,
if
if
let's
let's
say
say
my
my
density is
density is
constant
constant
throughout the
throughout the
body,
body,
so
so
I
I
have
have
this
this
body,
body,
and
and
in this
in this
body the
body the
density is
density is
constant
constant
everywhere.
everywhere.
So
So
in
in
that
that
case,
case,
I will
I will
get
get
x
x
dV
dV
divided by
divided by
volume.
volume.
So
So
this is
this is
actually the
actually the
centroid,
centroid,
and I
and I
can
can
further
further
get
get
x
x
p
p
dA.
dA.
So I
So I
can
can
write
write
volume
volume
as
as
some
some
thickness of
thickness
the
of the
body
body
multiplied by
multiplied by
area.
area.
So
So
if my
if my
thickness is
thickness is
uniform,
uniform,
thickness is
thickness is
not
not
changing at
changing at
all.
all.
For
For
example,
example,
disc.
disc.
So
So
let's
let's
assume
assume
that the
that the
thickness of
thickness of
this
this
disc
disc
is
is
not
not
changing
changing
and
and
it
it
is
is
T
T
everywhere.
everywhere.
In
In
that
that
case,
case,
this
this
relation
relation
now
now
reduce to
reduced to
centroid of
centroid of
this
this
area.
area.
So it
So
will
it will
be
be
x
x
dA
dA
by A.
by A.
And
And
in the same
in the
fashion,
same
we can
fashion, we can
actually
actually
reduce to
reduce
this
to this
expression from
expression
the
from the
area
area
expression.
expression.
So this
So these
all
all
expressions are
expressions are
related to
related
each
to
other,
each other,
and
and
this
this
expression we
expression
will
we
be
will be
using
using
to
to
calculate
calculate
the
the
location of
location
the
of the
resultant
resultant
force
force
which will
which will
act
act
on
on
the
the
any
any
kind of
kind
a
of a
beam.
beam.
So
So
just to
just to
understand the
understand the
concept,
concept,
let's
let's
solve
solve
the
the
first
first
question
question
where
where
we
we
have to
have to
find
find
the
the
sinusoid
sinusoid
x
x
bar.
bar.
Sorry,
Sorry,
y
y
bar.
bar.
So
So
basically,
basically,
we need
we
to
need to
find
find
this
this
sinusoid
sinusoid
which
which
in the
in
y
the y
direction,
direction,
and we
and we
just see
just see
the
the
expression
expression
that
that
the
the
location of the
location of the
center of
center of
gravity
gravity
can be
can be
given
given
by
by
twice this
this
expression,
expression,
which is
which is
just a
just a
moment
moment
balance.
balance.
So
So
the
the
left
left
side
side
movement is
movement is
due to
due to
the
the
weight of
weight
this
of this
object,
object,
overall
overall
weight,
weight,
and
and
the
the
right
right
side
side
is
is
due to
due
the
to the
summation of
summation of
weight
weight
due to
due to
the
the
summation of
summation
the
of the
particle
particle
which
which
present
present
inside
inside
this
this
object.
object.
And
And
we have
we have
given
given
its
its a
dimension.
dimension.
So
So
base
base
is
is
b,
b,
height
height
is
is
h,
h,
and the
and the
area
area
will
will
be
be
area of
area of
this
this
triangle
triangle
will
will
be
be
bh
bh
by
by
2,
2,
and
and
we
we
need to
need to
find
find
this
this
distance
distance
as
as
well,
well,
because
because
this
this
will
will
be
be
used to
used to
find the
find the
area.
area.
So the
So the
area of
area of
this
this
small
small
strip
strip
is a
is a
dA,
dA,
and
and
it
it
can be
can be
given
given
as
as
x
x
multiplied by
multiplied by
dy.
dy.
So
So
this is
this is
my
my
x
x
multiplied by
multiplied by
this
this
vertical
vertical
direction,
direction,
which
which
is
is
my
my
dy.
dy.
So
So
the
the
x
x
can be
can be
given as,
given
so
as,
we
so we
can
can
use the
use the
law of
law of
triangle,
triangle,
where
where
I
I
can
can
take the
take the
ratio
ratio
of the
of the
base
base
and
and
height of
height
the
of the
triangle.
triangle.
So
So
my
my
base is
base is
b
b
and
and
height
height
is
is
h,
h,
equal
equal
to,
to,
now
now
I
I
will
will
take
take
the
the
base
base
here,
here,
which
which
is
is
x,
x,
and
and
height
height
of
of
this,
this
or
or
sorry,
sorry
on
on
this,
this,
yeah,
yeah,
height of
height of
this
this
direction,
direction,
which
which
is
is
my
my
h
h
minus
minus
y.
y.
So
So
this is
this is
my
my
y,
y,
and my
and my
total
total
height
height
is
is
h.
h.
So
So
this
this
will
will
be
be
h
h
minus
minus
y.
y.
So
So
now I
now I
can
can
actually
actually
find
find
x,
x,
which
which
is
is
b
b
h
h
minus
minus
y
y
by
by
h.
h.
So
So
now
now
we
we
can
can
use
use
this
this
moment
moment
relation
relation
to
to
find
find
the
the
y
y
bar,
bar,
which
which
is
is
y
y
bar
bar
bh
bh
by
by
2
2
equals
equals
y,
y,
and
and
my
my
dA
dA
is
is
x
x
dy.
dy.
So
So
it
it
will
will
be
be
y
y
bar
bar
bh
bh
by
by
2
2
equals
equals
y,
y,
and
and
my
my
x
x
is
is
this.
this.
So
So
it
it
will
will
be
be
b
b
h
h
minus
minus
y
y
h
h
dy.
dy.
So
So
y
y
bar
bar
bh
bh
by
by
2.
2.
I
I
can
can
bring
bring
h
h
outside,
outside,
so it
so
will
it
be
will be
1 by
1 by
h,
h,
and it
and it
will
will
be
be
bh
bh
minus
minus
by
by
bh
bh
by
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 square,
square,
and I
and I
can
can
bring
bring
b
b
also
also
at
at
outside.
outside.
So
So
it
it
will
will
be
be
y
y
bar
bar
h by 2, 1 by h, and this will be h y square by 2 minus y cube by 3, and let's assign some units 0 to y, oh sorry, 0 to h. So it will be 1 by h cube by 2 minus h cube by 3, y by 2, it is h square because I take this h here. So it will be h by 2 minus h by 3, this is 6. So my y bar by 2 is equal to h by 6. So my y bar will be h by 3. So this is the location of center of gravity in the y direction. So for all the triangles, this is my distance, which is h by 3 from the base, and 2h by 3 from the top of the triangle. So this one can remember to find the increasing load when we are solving the force, or the linear load in x. For example, you might have encountered this kind of a load. So for that you need to find the location of the center of gravity, and it is from the base it will be always h by 3, and from the point it will be 2h by 3. So I need out in this one. So if not, then we can solve similar one again. So this time we need to find the centroid x bar and y bar. So first let's make the diagram here. And this is my elemental strip. This is x-axis, this is y-axis, and this curve is given by x equals ky cube. This is my length A, this is B, and this is the location we need to find. And my coordinate centroid will be this yc, which is pi by 2, and this is xc. So the length, area of this element will be y dx. This is my dx here. And to find the centroid in the x direction, we will be using x dx. So this is the centroid in the x direction, and my area will be given as integration of this curve. So area will be given as, it can be interpreted as area under the curve. So to find the area, so overall area can be given as 0 to a y dx. So this is my area of this whole curve. So it will be x 0 to a y dx, equals 0
0
to
to
a
a
xc
xc
y
y
dx.
dx.
So
So
I
I
can
can
get
get
y
y
from
from
this
this
relation,
relation,
equation
equation
of
of
this
this
curve,
curve,
which
which
is
is
x
x
equals
equals
k
k
y
y
cube.
cube.
So
So
my
my
y
y
will
will
be
be
x
x
by
by
k,
k,
and
and
y
y
will be
will be
then
then
x
x
by
by
k
k
1
1
by
by
3.
3.
Now
Now
we
we
can
can
actually
actually
also
also
get
get
k,
k,
because we
because
have
we have
given
given
x
x
equals
equals
to
to
k
k
y
y
cube,
cube,
and we
and we
have
have
also
also
given the
given the
dimensions.
dimensions.
So if
So
I
if I
put
put
x
x
equals
equals
a,
a,
then
then
b
b
equals
equals
b.
b.
So
So
my
my
k
k
will
will
be
be
a
a
by
by
b
b
cube.
cube.
So
So
now
now
we
we
can
can
solve
solve
this
this
expression.
expression.
So we
So we
will
will
have
have
x
x
bar
bar
0
0
to
to
a
a
x
x
by
by
k
k
1
1
by
by
3
3
dx
dx
equals
equals
x
x
4
4
by
by
3,
3,
and
and
this
this
is
is
k
k
1
1
by
by
3
3
dx
dx
from
from
0
0
to
to
a,
a,
because
because
it
it
will
will
be,
be,
so
so
this
this
expression will
expression
be
will be
like
like
x
x
multiply
multiply
x
x
1
1
by
by
3,
3,
so it
so it
will
will
give
give
us
us
x
x
4
4
by
by
3.
3.
So
So
when you
when you
solve
solve
this,
this,
you will
you will
get,
get,
so
so
yeah,
yeah,
it's
it's
from
from
0
0
to
to
a.
a.
So
So
when you
when you
solve
solve
this,
this,
you
you
get
get
x
x
bar
bar
3ab
3ab
by
by
4
4
equals
equals
3a
3a
square
square
b
b
by
by
7.
7.
So
So
here I
here I
put
put
k
k
as
as
a
a
by
by
b
b
cube,
cube,
which
which
we
we
found,
found,
and the
and the
x
x
bar
bar
will
will
be
be
a,
a,
b we
b we
cancel,
cancel,
3
3
3
3
cancel,
cancel,
and it
and it
will
will
be
be
4
4
by
by
7
7
a.
a.
So
So
this is
this is
our
our
x
x
bar,
bar,
and we
and we
can
can
repeat the
repeat the
same
same
procedure
procedure
for the
for the
y
y
bar.
bar.
So
So
for the
for the
centroid
centroid
in the
in the
y
y
direction,
direction,
it
it
will be
will be
y
y
a
a
integration
integration
ycdA.
ycdA.
Now
Now
we
we
can
can
we
we
know
know
yc
yc
is
is
y
y
by
by
2,
2,
so
so
it
it
will
will
be
be
y
y
bar
bar
0
0
to
to
a,
a,
and
and
this
this
will
will
be
be
y
y
dx
dx
y
y
by
by
2
2
y
y
dx.
dx.
So
So
we
we
already know
already know
this
this
term
term
from
from
the
the
above
above
calculation,
calculation,
which
which
is
is
this
this
actually,
actually,
except
except
for the
for the
x
x
bar
bar
case,
case,
we
we
can
can
write
write
directly
directly
y
y
bar
bar
3ab
3ab
by
by
4,
4,
and
and
this will
this will
be
be
y
y
square
square
by
by
2
2
dx.
dx.
And
And
y
y
is
is
given
given
as
as
x
x
by
by
k
k
to the
to the
power
power
1 by
1 by
3.
3.
So the
So the
y
y
square
square
will
will
be
be
x
x
by
by
k
k
2 by
2 by
3,
3,
to the
to the
power
power
2 by
2 by
3.
3.
So
So
3ab
3ab
y
y
bar
bar
by
by
4,
4,
and this
and this
is
is
x
x
by
by
k
k
cube
cube
2 by
2 by
3
3
dx.
dx.
So
So
when you
when you
integrate it,
integrate it,
you
you
will
will
get the
get the
y
y
bar
bar
as
as
2
2
by
by
5
5
b.
b.
So
So
this
this
is the
is the
y
y
bar,
bar,
and
and
this is
this
the
is the
x
x
bar.
bar.
So
So
basically,
basically,
you
you
need to
need to
use the
use the
moment
moment
balance
balance
equation,
equation,
and
and
in the
in the
both
both
direction,
direction,
x
x
and
and
y
y
direction, to
direction, to
calculate the
calculate the
centroid in
centroid in
both
both
direction.
direction.
In the
In the
previous
previous
one, we
one, we
use the
use the
moment
moment
balance
balance
in
in
only
only
one
one
direction, y
direction, y
bar,
bar,
Uh, so
So
you
you
can
can
use
use
multiple
multiple
times
times
in
in
order
order
to
to
get
get
the
the
sinusoid in
sinusoid
the
in the
multiple
multiple
direction.
direction.
So
So
any
any
issue.
issue.
So
So
just
just
to
to
go
go
ahead
ahead
solving
solving
problems,
problems,
let's
let's
see
see
how
how
to
to
calculate
calculate
the
the
general
general
load
load
in a
in a
varying
varying
if
if
you
you
have
are
given the
given the
varying
varying
load.
load.
So
So
for
for
example,
example,
this is
this
a
is a
beam
beam
and we
and
have
we have
given
given
this
this
varying
varying
load
load
here,
here,
and
and
let's
let's
say
say
the
the
equivalent
equivalent
load
load
is
is
R
R
here,
here,
which
which
is
is
acting
acting
on
on
in
in
this
this
location
location
from
from
X.
X.
So the
So the
location will
location
be
will be
X
X
bar
bar
from the
from the
origin,
origin,
and this
and this
R is
R
the
is the
resultant
resultant
force
force
of
of
this.
this.
So
So
this
this
curve
curve
is
is
can be
can be
given by,
given by,
let's
let's
say,
say,
dr
dr
w
w
dx.
dx.
So in
So in
order to
order to
find
find
the
the
resultant
resultant
force
force
of
of
this
this
uh,
uh,
force
force
which is
which is
varying in
varying
the
in the
x
x
direction,
direction,
it
it
can be
can be
given
given
as
as
w
w
dx,
dx,
and the
and the
location of
location of
this
this
force
force
from the
from the
origin
origin
is
is
the
the
same
same
sinusoid
sinusoid
expression
expression
w
w
dx
dx
divided by
divided by
r.
r.
So
So
this
this
two
two
equation
equation
we
we
will be
will be
using
using
to
to
calculate the
calculate the
resultant
resultant
force
force
of
of
this
this
varying
varying
load
load
as well
as
as
well as
the
the
location
location
of
of
this
this
resultant
resultant
from
from
force
force
from the
from the
origin.
origin.
And
And
this
this
expression
expression
is
is
already we
already
have
we have
seen
seen
it's a
it's a
centroid
centroid
expression,
expression,
and
and
this
this
expression
expression
uh,
uh,
is
is
actually the
actually the
area
area
under the
under the
curve.
curve.
So
So
this
this
W
W
is
is
actually
actually
has
has
the
a
unit
unit
of
of
Newton
Newton
per
per
length,
length,
and
and
the
the
rate
rate
of
of
change
change
of
of
W
W
in the
in the
x
x
direction
direction
actually
actually
giving
giving
you
you
this
this
R.
R.
So it
So
is
it is
basically
basically
area
area
which is
which is
making
making
by
by
this
this
curve.
curve.
So
So
this
this
whole
whole
area
area
is
is
actually
actually
represented
represented
by
by
a
a
single
single
point
point
force
force
which
which
is
is
R.
R.
It is
It
a
is a
resultant
resultant
force.
force.
So
So
we are
we are
actually
actually
uh,
uh,
what we
what
are
we are
doing.
doing,
We are
we are
taking the
taking the
equivalent of
equivalent of
this
this
whole
whole
varying
varying
force
force
into a
into a
single
single
point
point
force
force
which is
which is
acting in
acting in
on a
on a
very
very
specific
specific
point.
point.
And
And
therefore we
therefore we
needed
needed
two
two
things.
things.
First,
First,
the
the
magnitude
magnitude
of
of
that
that
single
single
force,
force,
and
and
second, the
second, the
location of
location of
that
that
force.
force.
So
So
that we
that we
will
will
see
see
when we
when we
solve
solve
these
these
kinds of
kinds
a
of a
problem.
problem.
So
So
let's
let's
solve
solve
this
this
simpler
simpler
problem
problem
first.
first.
So
So
here
here
we
we
need to
need to
determine the
determine the
normal
normal
force,
force,
shear
shear
force in
force
the
in the
bending
bending
moment
moment
at the
at the
given
given
point
point
B
B
and
and
C,
C,
and we
and we
have
have
given
given
a
a
external
external
force
force
which
which
is
is
acting
acting
on a
on a
beam
beam
which
which
is
is
6
6
kilonewton.
kilonewton.
So
So
first,
first,
let me
let
make
make
a
a
free
free
body
body
diagram.
diagram.
This is
This is
D,
D,
this
this
is
is
dy,
dy,
there
there
is
is
a
a
normal
normal
force
force
Ay,
Ay,
there is
there
a
is a
movement.
movement.
So
So
we
we
need to
need to
find the
find the
force
force
and
and
movement
movement
at a
at a
point B
point
and
B and
C.
C.
So
So
the
the
concept
concept
here
here
is
is
usually
usually
what we
what
do,
we
we
do, we
actually
actually
divide
divide
the
the
this
this
beam
beam
into
into
multiple
multiple
parts.
parts.
For
For
example,
example,
let's
let's
say
say
forget
forget
about
about
this
this
point B
point
and
B and
C.
C.
So
So
there is
there
a
is a
force
force
which is
which is
acting
acting
in
in
this
this
location.
location.
So
So
what
what
we
we
do,
do,
we
we
actually
actually
divide
divide
this
this
portion,
portion,
left
left
side of
side of
this
this
force,
force,
and
and
we
we
do the
do the
force and
force and
movement
movement
balance
balance
analysis.
analysis,
And
and
then
then
we
we
take the
take the
remaining
remaining
part
part
and do
and
the
do the
same
same
thing in
thing
the
in the
remaining
remaining
part.
part.
So
So
this
this
part
part
is
is
here in
here
the
in the
question
question
given
given
by
by
point
point
P,
P,
and
and
the
the
right
right
side
side
part
part
is
is
actually
actually
given by
given by
point
point
C.
C.
And
And
the
the
concept
concept
is
is
when we
when we
move
move
from
from
B
B
to
to
C,
C,
which
which
is
is
adjacent
adjacent
to
to
each
each
other,
other,
which is
which is
very
very,
very
very
close
close
to
to
each
each
other,
other.
what
What
is
is
the
the
variation in
variation
the
in the
shear
shear
force
force
as well
as
as
well
the
as the
bending
bending
moment
moment
diagram?
diagram?
So
So
that was
that
the
was the
concept
concept
here.
here.
So
So
when
when
you
you
actually
actually
move
move
from
from
left
left
side
side
of
of
this
this
point
point
force
force
to the right side of this point force here, there will be a jump in the shear force, which we will see while we are solving it. And therefore, there will be a sudden discontinuity in the shear force. And we can do this exercise for different, if there is a different loading, we can actually do the same exercise by splitting the beam into number of parts and calculating the force at the left side of that external force here, and then the right side of the force here. And in that way, we can actually keep getting the shear force at every part of this beam. So here in this beam we have only given 1 point force. So the calculation will be pretty much easy. So first we need to find the reactions AY. So let's take the movement along D, and the counterclockwise movement will be positive here. So and this movement will be acting all along the beam. For example, in the last topic, the first week class, somebody asked the question that if we have a movement here, can we consider that movement if we take the movement, let's say, in this direction? So this movement is actually valid in thoroughly through all the beam. So whatever the point you are choosing to take the movement, to do the movement balance, you need to consider all the movements here. So we have already given the movement here, external movement, which is 9 kilonewton meter, and if we are actually taking the movement at point D, then the movement will be created by this force AY by 6 kilonewton and by this movement. So instead of this movement, let's imagine if there is a force here. In that case, there will be no movement due to this force, because the distance, normal distance is 0 of this point force to D, because it is actually exerting at D. So there will be no movement due to this force. But if there is an external movement, then we need to consider that external movement here. So it will be AY. The distance is 3 meter, and this is 6 meter. So it will be 9. And 6 kilonewton is actually creating the counterclockwise movement. It is going counterclockwise movement along point D, so it is positive. And this 9 kilonewton external movement is actually also doing counterclockwise movement along point D, so it is also positive. So it will be minus 9 plus 36. So it will be 45 by 9. So my AY will be 5 kilonewton. So this is my normal reaction. Now let's split this part of the beam. So we are splitting this part of the beam in such a way that we are not considering this 6 kilonewton force. So basically we are in the region of B. We are actually considering a point B and not 6 kilonewton force first. So my beam will look like, this is my beam, this is A, and let's say this is some point B here. There is a vertical force which is, let's say, MB. Sorry, this is the horizontal force MB, and vertical force will be VB, and some movement will be there, MB. Because what happens, for example, you have this beam and you are actually putting some force here, so it will create a movement. But beam will try to resist here, and due to this resistance, it will create its own movement. Otherwise, it will start moving along this point. But this is not happening because the beam is fixed in both the ends. So it will create movements in all this direction, which is opposite to this movement, because there is a force which tries to rotate this beam, right? And this here, since the beam is fixed here, it will create counter movement. So this is actually the counter movement and counter forces, which is acting at location B. So now we do the force balance in this beam. So my horizontal force is 0 because this is my only horizontal force. And the vertical force is Ay minus Vb equal to 0, which gives us Ay equals to Vb. So my Vb will be Ay, which is 5 kilonewton. And then we can do the moment balance at point P. So we have Ay, and this distance is 3 meter. 3. So this is minus, this is plus, equal to 0. And my moment at B will be Ay, 3 Ay, which is 15 kilonewton. So this is my moment at B. Okay. Now let's consider this force also. So now we are just moving little ahead here, and we are actually considering this force as well. Just we are shifting very little to this force. So now we consider this force. This is my Ay, and let's say this is the force VC, and C, and there is a moment, and this is 6 kilonewton, and this is 3 meter. So now we take account of this force. We just move little ahead. We are not changing much the horizontal direction. So now if we do the force balance, Fx equal to 0, which will give NC, which is 0. Now force balance in the y direction will be Ay minus 6 minus Vc equal to 0. So Ay minus 6 equals to Vc, and Ay is 5. So my Vc will be minus 1 kilonewton. So this is my Vc, which has the direction of this, because we got minus 1 kilonewton. And now we will do moment balance at point C. So we will get, so the moment is actually coming from Ay. It is creating a moment which is clockwise around C, and this moment MC, which is counterclockwise around C, and there will be no movement from this force because it is exactly acting on that point. And therefore there is no normal distance. The normal distance is 0. So it is like 6 multiplied by 0, and there will be 0 movement from this force. So it will be Ay minus, this will be NC equals 0. So it will be 3Ay, and the moment here is 15 kilonewton meter. So now we can see that the moment at B, just little light, just little left from this point force is 15, and just little right from the point force is also 15. So movement is not changing due to this point force. Movement is same here, but the force, the vertical force Vb, which was 5 kilonewton, it got changed to minus 1 kilonewton. So here my force was 5 kilonewton, just little left from 6 kilonewton force here, and when we go to little right, the force will become minus 1 kilonewton. So there is a sharp jump in the vertical shear force. So for example, this is my 5 kilonewton. It was 5 kilonewton till B, and after B it
will
become
become
minus 1.
-1.
So
So
this
this
is
is
my
my
shear
shear
force
force
diagram,
diagram,
and the
and the
bending
bending
moment
moment
remains
remains
same.
same.
It
It
doesn't
doesn't
change at
change
all
at all.
in
In
case
case
of
of
a
our
in
in
case of
case
this
of this
problem
problem
where we
where
have
we have
only
only
point
point
force.
force.
So
So
any
any
doubt
doubt
in
in
this
this
one?
one?
Okay,
Okay,
then
then
let's
let's
move to
move
the
to the
next
next
one.
one.
Then.
Then.
So
So
now
now
we
we
are
are
solving
solving
uh,
uh,
a
a
problem
problem
where we
where
have
we have
a
a
load
load
which is
which is
varying
varying
in the
in the
x
x
direction.
direction.
So we
So we
need to
need to
find
find
the
the
forces and
forces and
movement
movement
at
at
this
this
point,
point,
at
at
point
point
C.
C.
So
So
here
here
my
my
force
force
per
per
unit
unit
length
length
will
will
be
be
4
4
kilonewton
kilonewton
per
per
meter.
meter.
So
So
as
as
usual,
usual,
first we
first we
need to
need to
find the
find the
normal
normal
reaction,
reaction,
which
which
is,
is
let's
let's
say
say
here AY,
AY,
and
and
here it
here it
is
is
BY.
BY.
So we
So we
need to
need to
calculate the
calculate the
normal
normal
reaction
reaction
first,
first,
and we
and we
need
need
to
to
uh,
uh,
solve
solve
this
this
varying
varying
load
load
into
into
a
a
single
single
point
point
force.
force.
So
So
there,
there,
so
so
this
this
varying
varying
load
load
can be
can be
represented
represented
by
by
some
some
point
point
force,
force,
let's say
let's say
that,
that
which
which
is
is
R.
R.
And
And
as
as
we
we
discussed,
discussed,
we
we
need the
need the
magnitude of
magnitude of
this
this
R
R
as well
as
as
well
the
as the
location,
location,
which
which
is
is
x
X
bar.
bar.
And we
And we
already
already
have
have
seen
seen
the
the
formula
formula.
to
To
find the
find the
R.
R,
It
it
is
is
W
W
dx,
dx,
and to
and to
find the
find the
location
location
from the
from the
base,
base,
it
it
is
is
x.
X,
Sorry,
sorry,
it
it
is
is
W
W
dx
dx
divided
divided
by
by
R.
R.
So
So
for
for
this
this
kind of a
kind of a
triangular
triangular
load, we
load, we
can
can
actually
actually
easily
easily
access.
access.
So
So
this
this
formula,
formula,
as we
as
have
we have
discussed,
discussed,
this is
this is
actually the
actually the
area
area
under the
under the
curve,
curve,
which
which
means
means
the
the
resultant
resultant
magnitude of
magnitude
the
of the
resultant
resultant
force
force
is
is
nothing
nothing
but
but
this
this
area
area
under
under
this
this
curve.
curve.
So
So
this
this
area,
area,
which is
which is
basically the
basically the
area of
area of
triangle,
triangle,
actually
actually
gives you
gives
the
you the
magnitude of
magnitude
the
of the
resultant
resultant
force,
force,
which
which
is
is
this
this
shown by
shown by
this
this
expression.
expression.
So the
So the
area of
area of
triangle
triangle
can be
can be
given
given
by
by
1
1
by
by
2
2
base
base
multiply by
multiply by
height.
height.
So
So
my
my
R
R
is
is
just
just
half.
half.
Now
Now
base is
base is
this.
this.
This is
This is
my
my
base of
base
the
of the
triangle,
triangle,
which
which
is
is
W,
W,
and then
and
it is
it is
given
given
as
as
4
4
kilonewton
kilonewton
per
per
meter.
meter.
4,
4.
and
And
this is
this
my
is my
height,
height,
which
which
uh,
uh,
which
which
is
is
6
6
meter.
meter.
6,
6.
so
So
it
it
will
will
be
be
12
12
kilonewton.
kilonewton.
So
So
my
my
R
R
is
is
12
12
kilonewton. So
kilonewton. So
this
this
is
is
12.
12.
And
And
in the
in the
first
first
problem, we
problem, we
see
see
that the
that the
centroid
centroid
from the
from the
base
base
can be
can be
given
given
by
by
h
h
by
by
3
3
from the
from the
base.
base.
So
So
this
this
centroid,
centroid,
here I
here
am
I am
writing with
writing with
x
x
bar.
bar.
This
This
x
x
bar,
bar,
the
the
location
location
of
of
this
this
resultant
resultant
force
force
is
is
actually
actually
h
h
by
by
3,
3,
which is
which is
6
6
by
by
3,
3,
which
which
is
is
2
2
meter
meter
from the
from the
base.
base.
So
So
this
this
is
is
2
2
meter.
meter.
So
So
now
now
this
this
problem
problem
converted
converted
into a
into a
point
point
force
force
problem,
problem,
where we
where
have
we have
here
here
A,
A,
B,
B,
and
and
there
there
is
is
R,
R,
which
which
is
is
2
2
meter
meter
from
from
A,
A,
and this
and
is
this is
some
some
location
location
C.
C.
This is
This
3
3
meter,
meter,
this
this
is
is
3
3
meter.
meter.
So
So
now we
now we
can
can
take a
take a
movement
moment
at
at
A
A
and
and
calculate the
calculate the
vertical
vertical
force
force
at
at
B.
B.
So the
So the
movement
movement
at
at
A
A
will
will
be
be
due
due
to
to
normal
normal
reaction
reaction
at
at
B,
B,
which
which
is
is
counterclockwise
counterclockwise
direction,
direction,
and
and
the
the
resultant
resultant
force
force
R,
R,
which
which
is
is
at
at
clockwise
clockwise
direction
direction
around
around
A.
A.
My R
My R
is
is
12,
12,
so
so
B
B
is
is
4
4
kilonewton.
kilonewton.
So this is
This
my
is my
normal
normal
reaction.
reaction.
So now
So
in
now in
order to
order to
find the
find the
force
force
at
at
C
C
at
at
location
location
C,
C,
let's
let's
split the
split the
beam.
beam.
So
So
this is
this is
my
my
C,
C,
this
this
is
is
BY,
BY,
this
this
is
is
some
some
moment,
moment,
and
and
this
this
is
is
my
my
the
the
location
location
here,
here.
which
It's
is
it's
BC, and
BC,
this
and this
is
is
horizontal
horizontal
force
force
NC,
NC.
and there
And
is
there
a
is a
varying
varying
load
load
here.
here.
Now
Now
we
we
actually
actually
identify
identify
this
this
R
R
because we
because
have
we have
given
given
the
the
varying
varying
load,
load,
which is
which is
varying
varying
from
from
point
point
A
A
to
to
point
point
P,
P.
and we
And we
actually
actually
calculate the
calculate the
resultant
resultant
force,
force,
which
which
is
is
R.
R.
Now
Now
we
we
actually
actually
cut
cut
this
this
beam
beam
into
into
half.
half.
We
We
cut
cut
this
this
beam,
beam,
but we
but we
don't know
don't
the
know the
location of
location of
this.
this.
So
So
here
here
we
we
know the
know the
location
location
of
of
force
force
per
per
unit
unit
length,
length,
which is
which is
4
4
kilonewton per
kilonewton per
meter.
meter.
But
But
here the
here
W,
W,
which
which
is
is
force
force
per
per
unit
unit
length,
length,
is
is
unknown
unknown
because
because
we
we
cut
cut
the
the
section
section
and
and
we
we
don't know
don't know
what
what
is the
is the
value of
value of
W
W
here.
here.
We
We
don't know
don't know
what is
what is
the
the
value of
value of
W
W
here,
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 and
and
anywhere
anywhere
else.
else.
So
So
again, we
again,
will
we will
use
use
the
the
law of
law of
triangle
triangle
where
where
we
we
write the
write the
ratio of
ratio of
base
base
and
and
height
height
of the
of the
triangle at
triangle at
different
different
locations.
locations.
So
So
at
at
A,
A,
it
it
is
is
4
4
by
by
6,
6,
and
and
at
at
C,
C,
it
it
is,
is,
let's say,
let's say,
WC
WC
by
by
3.
3.
So
So
this is
this
my
is my
base
base
for
for
at
at
A,
A,
which is
which is
4,
4,
and
and
WC is
WC
my
is my
base
base
at
at
point
point
C,
C.
and
And
6 is
6 is
my
my
overall
overall
height
height
from
from
point
point
A,
A,
and
and
3 is
3
the
is the
height
height
from
from
point
point
C
C
to
to
B.
B.
So
So
my
my
WC
WC
will
will
be,
be,
this
this
is
is
2,
2,
3,
3,
3,
3,
3
3
here,
here,
and
and
WC
WC
is
is
2
2
kilonewton
kilonewton
per
per
meter.
meter.
So
So
now
now
this
this
WC
WC
is
is
2
2
kilonewton
kilonewton
per
per
meter
meter
here.
here.
So
So
now
now
there will
there
be
will
a
be a
different
different
resultant
resultant
force.
force.
So the
So the
earlier
earlier
one,
one,
we
we
got
got
this
this
resultant
resultant
force
force
here,
here,
which
which
is
is
R,
R,
and which
and which
was
was
12
12
kilonewton.
kilonewton,
This
this
12
12
kilonewton.
kilonewton.
Now
Now
our
our
resultant
resultant
force
force
from the
from the
remaining
remaining
load,
load,
which
which
is
is
acting
acting
only
only
on
on
this
this
portion
portion
of
of
this
this
beam,
beam,
is
is
different.
different.
It
It
is,
is,
let's say,
let's say,
R1
R1
here,
here,
and we
and we
know
know
that
that
if we
if we
use
use
this
this
formula to
formula to
calculate the
calculate the
resultant
resultant
force,
force,
basically we
basically
are
we are
just
just
calculating the
calculating the
area
area
under the
under the
W.
W.
So
So
now to
now to
calculate
calculate
R1,
R1,
it's
it's
area
area
of
of
triangle,
triangle,
which
which
is
is
WC
WC
multiplied
multiplied
by
by
3.
3.
So
So
1
1
by
by
2.
2.
W
W
is,
is,
we
we
got
got
2
2
here.
here.
This
This
is
is
2,
2,
3.
3.
So my
So my
R1
R1
is
is
3
3
kilonewton.
kilonewton.
So
So
now we
now we
can do
can
the
do the
force
force
balance
balance
analysis.
analysis.
So
So
here
here
NC
NC
is
is
0.
0.
In the
In the
vertical
vertical
direction, my
direction, my
force
force
will
will
be
be
due
due
to
to
minus
minus
Vc
Vc
minus
minus
R1
R1
plus
plus
Dy
Dy
equal to
equal to
0.
0.
So
So
my
my
Vc
Vc
will
will
be
be
By
By
minus
minus
R1,
R1.
and
In
By
By
we
we
got
got
4
4
kilonewton
kilonewton
minus
minus
R1.
R1.
R1
R1
is
is
3.
3.
So my
My
Vc
Vc
is
is
1
1
kilonewton.
kilonewton.
Now
Now
we do
we
the
do the
moment
moment
balance
balance
analysis
analysis
along
along
this
this
point
point
C.
C.
So
So
we
we
will
will
have
have
minus
minus
NC
NC
plus
plus
By3
By3
and
and
R1
R1
is
is
again in
again
the
in the
clockwise
clockwise
direction
direction
along
along
point
point
C.
C.
So it
So it
is
is
minus
minus
R1,
R1
and the
and the
location is
location is
again,
again,
let's say
let's say
x
X
bar
bar
1,
1,
which
which
is
is
h1 by
H1 by
3,
3
and
and
h1 is
H1 is
3.
3.
So
So
my
my
x
X
bar
bar
1
1
is
is
just
just
1
1
meter.
meter.
So
So
it's
it's
1
1
meter
meter
from
from
this
this
base,
base.
which is
So
1
1
equal to
equal to
0.
0.
Then the
And the
moment
moment
at
at
C
C
will
will
be
be
By
By
is
is
4,
4
3,
and
my
my
R1
R1
is
is
3.
3.
It
This
is
is
9
9
kilonewton
kilonewton
meter.
meter.
So
So
this
this
is the
is the
movement
movement
at
at
C,
C
and
and
this
this
is
is
the
the
force at
force at
C.
C.
So
So
just to
just to
recap,
recap,
so we
so
have
we have
given the
given the
load
load
which is
which is
varying in
varying
the
in the
x
X
direction,
direction,
and
and
we
we
can
can
actually
actually
convert
convert
that
that
force
force
which is
which is
varying
varying
into a
into a
single
single
point
point
force,
force,
and
and
for
for
that we
that we
need to
need to
find
find
the
the
magnitude of
magnitude of
that
that
point
point
force and
force
the
and the
location
location
of
of
that
that
point
point
force.
force.
The
The
magnitude
magnitude
is
is
just the
just the
area
area
under the
under the
curve,
curve,
and the
and the
location is
location is
given by
given
the
by the
sinusoidal
sinusoidal
expression.
expression.
So
So
by
by
converted
converted
into a
into a
point
point
force
force
which
which
is
is
given in
given
this
in this
diagram,
diagram,
we
we
calculate the
calculate the
reaction
reaction
force
force
which is
which is
By.
By.
Then in
Then in
order to
order to
calculate the
calculate the
shear
shear
force
force
and the
and
moment
moment
at
at
point C,
point C,
we
we
cut the
cut the
beam,
beam,
this,
this,
and we
and we
consider
consider
this
this
part of
part
the
of the
beam.
beam.
And
And
then we
then
do
we
the
do the
movement and
movement and
force
force
balance
balance
analysis.
analysis.
Because in
Because in
this
this
part,
part,
my
my
force will
force
be
will be
again
again
radial.
radial.
So
So
this is
this
my
is my
C and
C
this
and
is
this is
B.
B.
And
And
again,
again,
my
my
resultant
resultant
force will
force
be
will be
different
different
because
because
this
this
is
is
W.
W.
Earlier
Earlier
it
it
was
was
4
4
kilonewton
kilonewton
here
here
at
at
A,
A,
but
but
now
now
at
at
C it
C
is
it is
some
some
unknown
unknown
W.
W.
Therefore,
Therefore,
my
my
resultant
resultant
force
force
now
now
will
will
change,
change,
and
and
my
my
centroid, the
the
distance
distance
of the
of the
resultant
resultant
force
force
from the
from the
base
base
will
will
also
also
get
get
changed.
changed.
So
So
we
we
again do
again
the
do the
similar
similar
exercise. We
exercise. We
again
again
use
use
this
this
equation to
equation to
calculate the
calculate the
equivalent
equivalent
resultant
resultant
force and
force
the
and the
location of
location
it.
of it.
And
And
then we
then we
again,
again,
once we
once we
got the
got the
resultant
resultant
force,
force,
then we
then we
again do
again
the
do the
force
force
balance
balance
analysis,
analysis,
and we
and
do
we
the
do the
moment
moment
balance
balance
analysis
analysis
to
to
calculate
calculate
these
these
quantities
quantities
at
at
a
a
specific
specific
point.
point.
So
So
any
any
question?
question?
The properties of diagonal that you mentioned
Yeah.
4 by yeah that 24 by 6.
Yeah,
Yeah,
we are
we are
just
just
use
use
actually we
actually
are
we are
using
using
the
the
linearity
linearity
relation.
relation.
So
So
the
the
force
force
is
is
actually
actually
behaving
behaving
linearly
linearly
like
like
this.
this.
So
So
what we
what
are
we are
doing, we
doing,
are
we are
actually
actually
considering
considering
this
this
length
length
and
and
this
this
length,
length.
and we
And
are
we are
saying
saying
the
the
ratio of
ratio of
this
this
length
length
to
to
this
this
length
length
will be
will be
equal
equal
to
to
the
the
ratio
ratio
of,
of,
let's say,
let's say,
this
this
length
length
and
and
this
this
length,
length,
because
because
it's,
it's,
you
you
can
can
see
see
it's
it's
decreasing
decreasing
linearly,
linearly,
which
which
means
means
the
the
ratio of
ratio of
these
these
two
two
quantity
quantity
will
will
remain
remain
same.
same.
Okay, that's okay, but the base height you're taken is 4 kN, 4, right?
Yeah,
Yeah,
4,
4
because
because
this is
this
a
is the
4 4
4
kilonewton per
kilonewton per
meter.
meter.
This
This
is
is
the
the
base,
base,
which
which
is
is
actually
actually
represented by
represented by
4
4
kilonewton
kilonewton
here,
here.
and
And
here
here
this
this
is
is
represented by
represented by
W.
W.
So
So
this
this
height is
height is
actually
actually
the
the
force
force
per
per
unit
unit
length.
length.
Okay, but if my doubt is 4, um, how can I tell you? The then what about the force on the point B? It's 0.
Yeah,
Yeah,
it's
it's
0.
0.
Okay, okay. It's 0 means then
0
0
means
means
that
that
the this
this
varying
varying
load,
load,
the
the
force
force
due to
due to
this
this
varying
varying
load is
load is
0.
0.
There
There
might be
might be
some
some
external
external non
vertical
vertical
reaction
reaction
at
at
B
B
or
or
some
some
movement
movement
at
at
B,
B, but due to this
but due to this varying
varying
load,
load,
the
the
force is
force is
0.
0.
The
The
force is
force is
0
0
here.
here.
The
The
force
force
is
is
half,
half,
almost
almost
half
half
here
here
at
at
point
point
C.
C.
And due
And
to
due to
this
this
varying
varying
load, the
load, the
force is
force is
0
0
at
at
B.
B.
okay.
Because
Because
force is
force is
decreasing
decreasing
as
as
in
in
the
the
as we
as we're
moving in
moving
the
in the
horizontal
horizontal
direction.
direction.
So
So
Okay. Okay, success.
okay.
well, you
Well, you
can
can
use
use
some
some
books
books
here
here
like
like
the
the
one of
one
the
of the
good
good
book
book
is
is
Mariam
Mariam
and
and
Craig.
Craig.
So
So
you
you
can
can
actually
actually
refer to
refer to
that
that
book,
book,
or you
or you
can
can
refer
refer
to
to
Russell
Russell
as
as
well.
well.
So I
So I
will
will
write
write
the
the
name
name
of the
of the
book.
book.
So
So
these are
these are
some
some
books
books
that
that
you
you
can
can
refer
refer
in
in
order to
order to
solve
solve
more
more
questions.
questions.
So
So
let's
let's
move.
move.
Uh,
Uh,
so
so
let's
let's
move to
move
the
to the
next
next
problem.
problem.
So
So
again,
again,
now
now
we
we
have
have
a
a
uniformly
uniformly
varying
varying
load.
load.
We
We
have
have
a
a
load which
load which
is
is
again
again
linearly
linearly
varying,
varying,
but
but
now it
now it
is
is
varying
varying
in
in
both
both
the
in the
direction,
direction,
the
the
left
left
and
and
right
right
hand
hand
direction,
direction,
and this
and
is
this is
overhand
overhand
beam.
beam.
So we
So we
need to
need to
find the
find the
same
same
force and
force and
moment
moment
at
at
point
point
C.
C.
And
And
this
this
point
point
is
is
3
3
kilonewton
kilonewton
per
per
meter.
meter.
So
So
now we
now
have
we have
a
a
varying
varying
load
load
which
which
is
is
varying in
varying in
both
both
left and
left and
right
right
direction.
direction.
So we
So
can
we can
actually
actually
split
Split
this
this
reading
reading
load
load
into
into
two
two
parts.
parts.
First
First
is
is
this,
this,
and
and
second
second
part
part
is
is
this.
this.
So
So
from the
from the
first
first
part,
part,
there will
there
be
will
a
be a
resultant
resultant
force
force
here,
here,
which
which
is
is
here,
here,
let's say
let's say
R1,
R1,
having a
having a
distance
distance
of
of
x
x
bar
bar
1,
1,
and
and
from
from
the
the
right hand
right
side
hand
there
side,
will
there
be
will be
a
a
resultant
resultant
force
force
R2,
R2,
which is
which is
having a
having a
distance
distance
x
x
bar
bar
2
2
from the
from the
base.
base.
And in
And in
order to
order to
find
find
R1
R1
and
and
R2,
R2,
we
we
need to
need to
find the
find the
area.
area.
And to
And to
find the
find the
location, we
location, we
need to
need to
find its
find its
centroid,
centroid,
which
which
we
we
know
know
for the
for the
triangle,
triangle,
it is
it is
actually
actually
h
h
by
by
3
3
from
from
base.
base.
So
So
my
my
R1
R1
will be
will be
given
given
as,
as,
so
so
let's say
let's
this
say
is
this
my
is my
1.5,
1.5,
1.5
1.5
here,
here,
this is
this is
also
also
1.5.
1.5.
So my
So my
R1
R1
is,
is
will
will
be
be
this
this
distance
distance
plus,
plus,
sorry,
sorry,
multiply
multiply
by
by
this
this
base,
base,
which
which
is
is
3
3
kilonewton
kilonewton
meter.
meter.
So
So
my
my
area will
area
be
will be
1
1
by
by
2,
2,
3
3
multiply
multiply
by
by
1.5,
1.5,
1.5
1.5
plus
plus
1.5.
1.5.
So it
So it
will be
will be
just
just
6.75
6.75
kilonewton.
kilonewton.
So
So
this is
this
my
is my
R1,
R1,
and my
and my
R2
R2
will
will
be
be
1
1
by
by
2,
2,
1.5
1.5
multiplied by
multiplied by
3,
3,
so it
so it
is
is
4.5
4.5
by
by
2,
2,
which
which
is
is
2.25
2.25
kilonewton.
kilonewton.
So
So
now we
now we
need to
need to
find
find
the
the
vertical
vertical
reaction
reaction
AY
AY
or
or
BY.
BY.
So
So
when we
when we
take the
take the
movement
movement
at
at
BY,
BY,
the
the
movement will
movement
be
will be
caused
caused
due
due
to
to
AY,
AY,
which
which
is
is
clockwise,
clockwise,
R1,
R1,
which
which
is
is
anti-clockwise,
anti-clockwise,
and this
and this
R2,
R2,
which is
which is
again
again
clockwise.
clockwise.
So this is
This is
minus,
minus,
this is
this is
plus,
plus,
and this
and
is
this is
also
also
minus.
minus.
So it
So it
is
is
minus
minus
AY
AY
multiplied by
multiplied by
3
3
plus
plus
R1
R1
multiplied by,
multiplied by,
so my
so my
X
X
bar
bar
will
will
be,
be,
X1
X1
bar
bar
will
will
be
be
uh, 4.5
4.5
by
by
3,
3,
which
which
is
is
1.5
1.5
meter,
meter,
and
and
X2
X2
bar
bar
will
will
be
be
1.5
1.5
by
by
3,
3,
which
which
is
is
zero
zero
point
point
5
5
meter
meter
from the
from the
base.
base.
So
So
this
this
both
both
distance
distance
are
are
from
from
this
this
base
base,
3, which is
which is
at
at
B.
B.
So my
So my
R1
R1
is
is
multiply
multiply
with
with
1.5
1.5
minus
minus
R2
R2
multiply
multiply
by
by
zero
zero
point
point
0.5.
0.5.
So my
So my
3
3
AY
AY
equals
equals
to
to
6.75
6.75
multiplied by
multiplied by
1.5,
1.5,
2.25,
2.25,
So this will
This
be
will be
9
9
by
by
3,
3,
which
which
is
is
AY
AY
will
will
be
be 3,
3
3
kilonewton.
kilonewton.
This
This
is
is
our normal
normal
reaction
reaction
at
at
A.
A.
So
So
now we
now
split the
split the
beam.
beam.
So
So
we
we
split the
split the
beam
beam
here,
here,
and we
and we
only
only
consider
consider
this
this
part of
part
the
of the
beam.
beam.
And
And
this, you
this you
can
can
see
see
this
this
resultant
resultant
force
force
R1,
R1,
which
which
is
is
acting
acting
1.5
1.5
meter
meter
from
from
uh,
B,
B, which
which
means
means
that
that
this
this
actually
actually
resultant
result in
acting on
acting on
C
C
itself.
itself.
So
So
this is
this
my
is my
R1.
R1.
So
So
this
this
resultant
resultant
force
force
R1, which
R1,
is
which is
acting
acting
on
on
C. So
C. So
let's
let's
consider
consider
this
this
force
force
as
as
also.
also.
So
So
if we
if we
consider
consider
only
only
part
part
AC,
AC,
then
then
we
we
will
will
have
have
some
some
kind of
kind
a
of a
trapezoidal
trapezoidal
load
load
here.
here.
So
So
we
we
need
need
to
to
split
split
this
this
load
load
into
into
one
one
triangular
triangular
and
and
one
one
square
square
load.
load.
So
So
just
just
to
to
make
make
it
it
little
little
simple,
simple,
let's
let's
consider
consider
this
this
whole
whole
portion
portion
of
of
this
this
beam.
beam.
So
So
let's
let's
say
say
my
my
extreme
extreme
left
left
is
is
D
D
and the
and the
extreme
extreme
right is
right is
C.
C.
So we
So
are
we are
considering
considering
DC
DC
part
part
of
of
this
this
beam.
beam.
So
So
this
this
is
is
AY,
AY,
this is
this is
C,
C,
this
this
is
is
VC,
VC,
this is
this
my
is my
horizontal,
horizontal,
and this
and
is
this is
movement
movement
at
at
C,
C.
and
And
there
there
is
is
some
some
load
load
which
which
is
is
linearly
linearly
varying,
varying,
and this
and
is
this
my
is my
W
W
naught,
naught,
let's
let's
say,
say,
and
and
this is
this is
1.5
1.5
meter,
meter,
this is
this is
1.5
1.5
meter.
meter.
Now we
Now we
need to
need to
find a
find a
W
W
naught.
naught.
So
So
again,
again,
by
by
law of
law of
triangle,
triangle,
we
we
need to
need to
find
find
this
this
W
W
naught.
naught.
So
So
again, we
again,
can
we
take
can
the
take the
ratio
ratio
based by
based by
height.
height.
So it
It
is
is
at
at
point
point
B,
B,
it
it
is
is
equal
equal
to
to
3
3
by
by
4.5
4.5
equal
equal
to
to
WC
WC
by,
by,
sorry,
sorry,
W
W
naught,
naught,
W
W
naught
naught
by
by
3.
3.
So
So
my
my
W
W
naught will
naught will
be
be
9,
9,
4.5,
4.5,
3,
3,
1.5.
1.5.
So it
So
will
it
be
will be
2.
2.
So
So
W
W
naught
naught
is
is
2
2
kilonewton
kilonewton
per
per
meter.
meter.
So
So
there
there
will be
will
a
be a
resultant
resultant
force
force
here,
here,
which
which
is
is
2
2
kilonewton.
kilonewton.
Sorry,
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 sorry.
sorry.
W
W
naught is
naught
2
is 2
kilonewton.
kilonewton.
Sorry.
Sorry.
So to
To
find the
find the
resultant
resultant
force
force
here
here
in
in
this
this
part of
part
the
of the
beam,
beam,
we have
we
to
have to
take the
take the
area,
area,
which
which
is
is
W
W
naught
naught
multiplied
multiplied
by
by
3,
3,
which is
which
the
is the
total
total
distance.
distance.
So
So
my
my
R
R
is
is
3
3
kilonewton.
kilonewton.
So
So
here the
here the
resultant
resultant
force
force
is
is
3
3
kilonewton,
kilonewton,
and the
and the
distance
distance
from the
from the
centroid
centroid
is,
is,
sorry,
sorry,
distance
distance
from the
from the
base,
base,
which is
which is
point
point
C,
C,
is
is
3
3
by
by
3,
3,
which
which
is
is
1
1
meter.
meter.
So
So
this
this
is
is
1
1
meter.
meter.
So if
So
we
if
do
we
the
do the
force
force
balance,
balance,
we
we
have
have
AY,
AY,
which
which
is
is
3
3
minus
minus
VC
VC
minus
minus
R
R
equal to
equal to
0.
0.
So
So
VC will
VC
be
will be
3
3
minus
minus
R,
R,
and my R is 3. So my force at point C is 0 kilonewton, and one can find the moment also at point C. So it will be minus AY 1.5 plus R1, which is 1 meter from C, plus movement at C. So the movement at C will be AY is 3 kilonewton, 1.5, R1 is, or R is again 3 kilonewton, so my movement is 1.5 kilonewton meter in the counterclockwise direction. So this is my movement at C, and this is my force at C. So just to recap, this is the same problem that we have solved in the last question. It's just that now we have a linear varying load in the both direction, in the left side direction and the right side direction, right and left, and we split this force into two triangles. So now there will be a two resultant force, and from the area under the curve we can find the magnitude of those two resultant force. So we found those two resultant force just to calculate the normal reaction. Once we get the normal reaction, which we have got AY, then we split the beam. We split this DC part of the beam, and then we do the similar exercise. We calculate the new normal reaction, which is due to this part only, which is only due to this part. And we found the location of this resultant force from the base, and do the moment and force balance analysis to calculate the force and moment at point C. You can consider this part of the beam as well. So it is actually arbitrary. So we consider this part just to simplify our calculation. If you consider the right hand side, then again you need to calculate this triangular load and the force due to this trapezoidal load. And to calculate the force due to trapezoidal load, you need to again split into this triangle and this square. So it will be a little cumbersome exercise. So I need out. If not, then we can move to the next. So in this problem, we need to find the normal reaction at point A. And there is a varying load. At A it is 1000 Newton per meter, and at B it is 2024 Newton per meter. And the load is varying as W naught kx cube. So again we need to find some resultant force of this varying load. So this is my some varying load which is acting here, and
and
there
there
will be
will be
some
some
resultant
resultant
force
force
which
which
is
is
acting
acting
here.
here.
And we
And we
know
know
that the
that the
resultant
resultant
force
force
will be
will be
given
given
by
by
area
area
under the
under the
curve
curve
and
and
its
its
centroid
centroid
is
is
from the
from the
moment
moment
equation.
equation.
So in
So
the
in the
above
above
example,
example,
we
we
were
were
finding the
finding the
area
area
under the
under the
curve,
curve,
but
but
we
we
don't
don't
use
use
this
this
expression
expression
because
because
it
it
was
was
a
a
triangle
triangle
and we
and we
all
all
know
know
the
the
area
area
under
under
the
the
curve which
curve
is
which is
triangle,
triangle,
which
which
forms the
forms the
triangle,
triangle,
what is
what
the
is the
area.
area.
So
So
we
we
simply
simply
write the
write the
area of
area of
triangle.
triangle.
Similarly, if
Similarly,
the
if the
load
load
is
is
like
like
this,
this,
we
we
need to
need to
find the
find the
area
area
under
under
this
this
curve,
curve,
which is
which is the,
just a
just a
straight
straight
line.
line.
And we
And we
know
know
this
this,
what is
what
the
is the
area of
area of
this
this
rectangle, which
rectangle,
is
which is
basically the
basically the
area
area
under this
under this
curve.
curve.
So
So
basically,
basically,
my
my
area
area
of
of
rectangle
rectangle
equals
equals
to
to
WBX,
WBX,
and the
and the
same
same
equals
equals
to
to
B
B
multiply
multiply
H.
H.
For the
For the
triangle, it
triangle, it
is
is
BH
BH
by
by
2.
2.
So
So
in the
in the
above
above
problem, we
problem, we
don't
don't
need to
need to
evaluate
evaluate
this
this
integral
integral
quantity.
quantity.
Rather,
Rather,
we
we
directly
directly
write the
write the
area
area
in
in
terms
terms
of
of
base
base
and
and
height.
height.
But
But
here,
here,
we
we
have
have
given a
given a
curve.
curve.
And in
And in
order to
order to
find the
find the
resultant
resultant
force,
force,
we
we
need
need
to
to
use
use
this
this
relation.
relation.
So my
My
resultant
resultant
force
force
will
will
be
be
then
then
given
given
as
as
0
0
to
to
8
8
W
W
naught
naught
kx
kx
cube
cube
and
and
have to
have to
integrate
integrate
over
over
dx.
dx.
Now we
Now we
don't
don't
know the
know the
k,
k,
but we
but we
can
can
find the
find the
k
k
from the
from the
given
given
expression
expression
itself.
itself.
So for
So for
example,
example,
this is
this is
my
my
8
8
meter.
meter.
So
So
W
W
is,
is,
so
so
my
my
W
W
is
is
1000
1000
Newton
Newton
per
per
meter
meter
at
at
x
x
equals
equals
to
to
0,
0,
and
and
W
W
is
is
2024
2024
Newton
Newton
per
per
meter
meter
at
at
x
x
equals
equals
8
8
meter.
meter.
So
So
one
one
by
by
one we
one, we
need to
need to
put
put
this
this
condition
condition
here
here
in
in
this
this
expression.
expression.
So
So
when
when
x
x
equal to
equal to
0,
0,
my
my
W
W
is
is
1000.
1000.
So my
So my
W
W
naught will
naught will
be
be
1000
1000
here.
here.
Then
Then
when
when
x
x
is
is
8
8
meter,
meter,
then my
then my
W is
W is
2024.
2024.
My
My
W
W
naught is
naught is
1000
1000
plus
plus
k
k
8
8
cube.
cube.
So it
So it
is
is
2024
2024
minus
minus
1000
1000
equals
equals
k
k
8
8
cube.
cube.
So my
My
k
k
will
will
be
be
2.
2.
So
So
now the
now the
expression we
expression we
have
have
W
W
equals
equals
1000
1000
plus
plus
2x
2x
cube.
cube.
So
So
this is
this
the
is the
equation
equation
we
we
need to
need to
integrate.
integrate.
So
So
when
when
we
we
integrate it,
integrate it,
we
we
will
will
get
get
1000x
1000x
plus
plus
2x4
2x4
by
by
4.
4.
So
So
here I
here I
will
will
get
get
2
2
or
or
8 to
8
the
to the
power
power
4
4
by
by
2.
2.
So
So
on
on
solving
solving
this,
this,
we
we
will
will
get
get
R
R
as
as
10.05
10.05
kilonewton.
kilonewton.
So we have given a force in the Newton. I am writing in the kilonewton. And similarly, we can find the distance of this force from the base, which is x w dx by resultant force. So my resultant force is 10.05 10 to the power 3 Newton, and W is 1000 plus 2x cube dx. So when we integrate it, we get 1000 x squared by 2 plus 2x to the power 5 by 5. So when you solve this quantity, you will get x power as 4.49 Newton. So now this whole problem is become very easy now, because it become like, so now there is only one force R and force at A. Normal reaction at A. This is 4.49 that we have found here. So now, in order to find the reaction at A, we need to take the moment at A. I mean, one can find the moment at A from this. So here it is NA minus 4.49 equal to 0, 10.05 multiplied by 4.49, and my NA will be 45.1 kilonewton. And in order to find the force at A, we need to do the force balance. So it is AY minus R equal to 0. So my AY equals to R, which is 10.05 kilonewton. So this is my normal reaction at A, and this is my movement at A. So just we actually calculated the resultant force and the location of this resultant force from A, and then we have done the moment and force balance analysis. Any doubt? So let's move to the new problem. So before moving to the new problem, we actually can relate the shear force and the bending moment as well as the force per unit length into each other. So the force per unit length can be given as dV by dx, and from this expression we can write dV w dx. So which we are already using to find the resultant force, this one. Basically R is my shear force. So the shear force can be given by force per unit length and the curve which is area of this curve which is given under force per unit length, and the force per unit length is just the rate of change of shear force in the horizontal direction. Similarly, the shear force can also be written as dm by dx, which is the rate of change of bending moment in the horizontal direction. And from this relation we can write bending moment, which is actually the area under the shear force curve. So one can use this expression also to calculate the shear force and the bending moment. And we will see in the subsequent question that how to draw the shear force diagram as well as the bending moment diagram. So until now,
I have a doubt. In the previous some model, the force was mentioned as 4 kilonewton per meter like that only, right? But forces keep on varying all points, right? How?
yeah, so you mean this W, right? W. Yeah, so it is given kilonewton per meter. So it is varying. So this WZ is at the point. It is not the force throughout this curve. It is actually at a single point. If you change the point, the W will also get changed.
Okay, then what's the meaning for per meter there?
It's per meter, which means it's a force divided by length. So divided by length means a unit length force. You are actually specifying the force which is at a very specific point, and that's why you are dividing by whole length. And if you increase the length, or if you change the length, horizontal length, that force will be changing. The force per unit length will keep changing because we have given some certain nature of the force which is changing. So the only way to write is to write this force per unit length at each point. So this force per unit length is actually keep changing at each point.
Yes, keep changing, but I can't express my doubt about that.
So basically, see, you cannot write the force in terms of F, because then what happens that in an entire length, the force will be same in an entire length. So you need to specify the force which become independent of a length. So you actually have to write the force at some point. So what you are doing, you are actually writing the force per unit length. So now you have a force, let's say, which is given by x square, and it is per unit length, which is x square by L. If you, let's say, if you take the elemental area, then your force will be x square by some elemental length dx. Now as you keep changing the horizontal length, this quantity, this elemental quantity keep changing. And this is actually represented by this whole one, not this alone x square.
So my doubt is then the force should change after a unit meter only should change, right?
Not the unit meter. I mean, it is variable in the horizontal direction. Because you can see this force. It is a function of x. This force is a function of x. So this whole quantity is actually, if you want to make it in a Newton, then you need to multiply this whole quantity by L. So this quantity will be kilonewton. And this will be length multiplied by some W. And you can change the length because this force is varying at each length. So you can actually specify the length until you need to find the force. So if you want to find force here, you need to consider this length. If you want to find here, you need to consider this length. So length is arbitrary. It is according at where you want to find the force.
Then the force at the point B is 2024 Newton per meter or 2024 multiple 8. What's the exact force at the B?
Yeah, it is at the B. It is
At the B,
2024
it
multiplied
is
by 8
2024
because
multiplied
it's
by 8
Newton per meter.
because Newton per
So
meter.
Newton per meter.
So
So if you
Newton per
multiply
meter.
by
So if
meter,
you
then
multiply
it
by
become
meter,
Newton.
then it become Newton.
So that's the value of the force at B. Then the point at A is 0, right? Then there is no load like
No,
this.
no,
No, no.
no. At A it is not zero.
At
It
A, it
is
is not zero. It is
sorry, yeah.
oh, sorry, yeah.
No,
No,
the
the
force
force
at A
at
is
A is
not
not
zero
zero
because
because
the
the
distribution is
distribution is
actually
actually
given by
given by
W
W
naught
naught
kx
kx
cube.
cube.
So
So
here we
here we
cannot
cannot
actually
actually
simply
simply
multiply by
multiply by
8.
8.
So in
So in
order to
order to
find the
find the
force
force
here,
here,
you
you
need to
need to
use
use
this
this
distribution.
distribution.
So
So
at
at
x
x
equal to
equal to
8,
8,
the
the
force
force
at
at
B
B
will be
will be
given
given
as
as
W
W
naught
naught
plus
plus
8
8
cube
cube
K.
K.
This will
This
be
will
the
be the
force
force
at
at
B.
B.
Sorry,
Sorry,
force
force
per
per
unit
unit
length.
length.
Yeah,
Yeah,
sorry.
sorry.
So
So
this will
this will
give
give
you
you
the
the
force
force
per
per
unit
unit
length.
length.
So
So
at
at
B
B
you
you
will
will
get
get
this
this
quantity
quantity
W
W
naught
naught
plus
plus
8
8
cube
cube
K.
K.
And
And
at
at
point
point
A
A
you will
you will
get
get
just
just
W
W
naught,
naught,
which is
which is
1000
1000
Newton per
Newton per
meter.
meter.
And there
And
is
there
a
is a
variation of
variation of
force
force
from
from
1000
1000
Newton
Newton
per
per
meter
meter
to
to
W
W
naught
naught
plus
plus
8
8
cube
cube
K.
K.
Okay, that's clear now.
And
And
yeah,
yeah,
and
and
this
this
quantity
quantity
is
is
actually
actually
represent
represent
this
this
height
height
of
of
this
this
loading.
loading.
And the
And the
overall
overall
force
force
actually
actually
given
given
by
by
area
area
under
under
this
this
loading.
loading.
So
So
to
to
find
find
the
the
overall
overall
force
force
at
at
point
point
B,
B,
you
you
need to
need to
find the
find the
area
area
under the
under the
curve
curve
here,
here
because
because
this
this
area,
area,
which is
which is
this
this
quantity, which
quantity,
is
which is
W naught
W naught
plus
plus
8 cube
8 cube
K,
K,
multiply
multiply
by
by
this
this
quantity,
quantity,
this
this
whole
whole
length.
length.
So
So
this
this
area
area
will
will
give you
give you
the
the
overall
overall
force
force
under the
under the
B.
B.
So for
So for
example,
example,
in
in
order to
order to
find the
find the
force
force
at
at
B,
B,
what you
what you
need to
need to
do,
do,
you
you
need to
need to
find the
find the
resultant
resultant
force
force
because
because
this
this
force
force
acting
acting
at
at
some
some
specific
specific
point,
point,
which
which
is
is
R,
R,
and when
and
you
when
do
you
the
do the
force
force
balance
balance
analysis, it
analysis,
will
it
be
will be
just
just
AY
AY
minus
minus
R.
R.
And
And
that we
that we
found
found
actually it
actually it
is
is
minus
minus
VB
VB
equal to
equal to
0.
0.
So
So
VB
VB
can
can
be
be
represented
represented
as,
as,
or
or
wait a
wait a
minute, we
minute, we
can
can
also
also
do
do
this
this
thing.
thing.
So
So
we
we
can
can
actually
actually
take
take
this
this
part of
part
the
of the
beam,
beam,
we
we
can
can
cut
cut
in
in
this
this
part of
part
the
of the
beam,
beam,
and we
and we
can
can
consider
consider
only
only
this
this
curve,
curve,
this
this
part of
part
the
of the
curve,
curve,
and we
and we
can
can
actually
actually
calculate
calculate
this
this
area.
area.
Once you
Once you
calculate
calculate
this
this
area,
area,
you will
you will
get a
get a
resultant
resultant
force
force
here
here
R,
R,
and
and
that
that
resultant
resultant
force
force
will be
will be
the
the
force
force
at
at
B
B,
and
and
everywhere,
everywhere,
basically
basically
everywhere
everywhere
in
in
this
this
direction.
direction.
Did you
Did you
understand
understand
this?
this?
So
Yes,
basically,
yes, yes.
yeah,
Yeah.
because
Because
you
you
cannot
cannot
just
just
multiply
multiply
here
here
with
with
some
some
length
length
and
and
we
we
just
just
define the
define the
overall
overall
force
force
here.
here.
We
We
need
need
to
to
calculate the
calculate the
area
area
under the
under the
curve
curve
to
to
define
define
the
the
force
force
just
just
near
near
adjacent to
adjacent to
the
the
point
point
B,
B,
because the
because the
curve
curve
is
is
non-linear
non-linear
in
in
nature.
nature.
So is
Is
it
it
clear?
clear? Yes, clear.
Okay,
Okay,
then
then.
so
So
let's
let's
move to
move to
this
this
question.
question.
So
So
here we
here we
need to
need to
actually
actually
find
find
the,
the,
draw the
draw the
shear
shear
force and
force and
bending
bending
moment
moment
diagram.
diagram.
Let's say
Let's say
this is
this is
R1,
R1,
R2,
R2,
this
this
is
is
4 and
4
this
and
is
this is
6
6
meter.
meter.
So
So
first we
first we
need to
need to
find
find
the
the
normal
normal
reaction.
reaction.
So
So
we
we
can
can
take
take
the movement
movement
along
along
R2.
R2.
So my
So my
R1
R1
is
is
1.6
1.6
kilonewton.
kilonewton.
And
And we,
when we
when
do
we
the
do the
force
force
balance
balance
analysis,
analysis,
we
we
will
will
get
get
R2
R2
as
as
4
4
minus
minus
R2,
R2,
which
which
is
is
4
4
minus
minus
1.6.
1.6.
So my
So my
R2
R2
will
will
be
be
2.4
2.4
kilonewton.
kilonewton.
So
So
let's
let's
consider
consider
this
this
part
part
of the
of the
beam
beam
first.
first.
Let's say
Let's say
this is
this is
BC,
BC,
this
this
is
is
horizontal,
horizontal,
and
and
this is
this
the
is the
movement.
movement.
Now,
Now,
and this
and this
is
is
6
6
meter.
meter.
So if
So
we
if
do
we
the
do the
force
force
balance
balance
analysis in
analysis in
this
this
part,
part,
we
we
will
will
have
have
C
C
equals
equals
0,
0.
and for
And
the
for the
vertical
vertical
one, we
one,
will
we will
have
have
1.6
1.6
minus
minus
VC
VC
equal to
equal to
0.
0.
So
So
VC
VC
will
will
be
be
1.6
1.6
kilonewton.
kilonewton.
Or
Or
let's
let's
say
say
this is
this is
some
some
arbitrary
arbitrary
part
part
which
which
is
is
cut.
cut.
So
So
this
this
distance
distance
is
is
x,
x,
not
not
6.
6.
So
So
if I
if
do
I
the
do the
movement
movement
balance
balance
at
at
point,
point,
at the
the
end
end
point
point
left
left
part,
part,
we
we
have
have
1.6
1.6
x
x
plus
plus
m at
m
the
at the
left
left
equal to
equal to
0.
0.
And it
And
will
it
be
will be
1.6x
1.6x
because I
because
am
I am
considering the
considering the
x
x
distance
distance
because
because
I
I
want to
want to
write
write
my
my
bending
bending
moment in
moment in
terms of
terms of
x.
x.
So
So
by
by
considering
considering
x, I
x,
am
I am
actually
actually
cutting
cutting
the
the
part which
part which
is
is
some
some
x
x
distance,
distance,
not
not
exactly
exactly
at
at
this
this
point,
point,
but
but
some
some
at
at
x
x
distance.
distance.
Now
Now
let's
let's
consider
consider
cutting the
cutting the
part
parts
some
on
this
this
one,
one,
and we
and
have
we
a
have a
distance.
distance.
This
This
distance
distance
is
is
10
10
minus
minus
x.
x.
The
The
overall
overall
distance
distance
is
is
10.
10.
And this
And
is the
this is the
part
part
actually
actually,
which which is 10 minus x. Let's say amount. This is VR. This is 2.4 kilonewton. Just for 2, and there is a force 4 kilonewton. Or let's say if we hit the force. Let's say we consider only this part, so we can emit this force, and the calculation become even more easy. So it will be 10 minus x, and this is m1, this is VR. So we are actually considering only this part. So my x is now the new x, not the previous x. So it will be n0 equal to 0. Fi will be 2.4 plus VR equal to 0 will be minus 2.4. So VR is this direction, and my movement will be minus mr plus 2.4 10 minus x plus 0 2.4 10 minus x equal to 0. So this is my movement at right hand side, and this is my movement at left hand side, and this is my shear force at right hand side, and this is my shear force at that was my shear force at left hand side, and this is my shear force at right hand side. So we can now draw the diagram. So this is my shear force. So at left it was 1.6. And it will remain 1.6 till we encounter this point load. So it will remain 1.6 till here, and from here it will be minus 2.4 that we found. And here it is minus 2.4. And for the DMD, you can actually use this equation that we found. So left it is 1.6x, and at the left it is 2.4 multiplied by 10 minus x. So you can see it's linear in x. So linear in x, and this is your point C. So it's this. Here it is this. So this is your 1.6, and this is your 2.4 10 minus x. It's linear in x, and therefore there will be a straight line. So this is your BMD. And you can inspect also, for example, this bending moment is 0 here, because the x is 10. So basically 10 minus 10, which is 0, multiplied by 2.4, which is 0. So bending moment will be 0 here. And here also it is 0 because x is 0. So we are multiplying 1.6 into 0. So as we increase the x, it will go here by obeying this formula. And from here, it will obey this equation which we found. So this
This
is
is
our
our
bending
bending
moment
moment
diagram,
diagram,
and
and
this is
this
our
is our
shear
shear
force
force
diagram.
diagram.
And
And
we in
we
the
in the
previous
previous
question
question
also
also
we
we
saw
saw
that
that
when we
when we
introduce the
introduce the
point
point
force,
force,
there is
there
a
is a
discontinuity
discontinuity
in
in
the
the
shear
shear
force
force
diagram.
diagram.
But
But
here
here
in
in
this
this
problem,
problem,
we
we
saw
saw
there
there
is
is
a
a
change in
change
the
in the
bending
bending
moment
moment
also.
also.
Earlier we
Earlier we
saw
saw
that
that
there
there
was
was
not a
not a
change,
change,
but
but
here we
here we
saw
saw
there
there
is
is
a
a
change
change
in
in
bending
bending
moment
moment
diagram
diagram
itself.
also.
So
So
any
any
doubt?
doubt?
So
So
in
in
order
order
to
to
draw
draw
this
this
shear
shear
force
force
and
and
bending
bending
moment
moment
diagram,
diagram,
basically
basically
you
you
need
need
to
to
find
find
this
this
vertical
vertical
force and
force
the
and the
bending
bending
moment
moment
at
at
each
each
point.
point.
So
So
if you
if
have
you are
given the
given the
point
point
load,
load,
you will
you
just
just
first
first
consider the
consider the
left
left
side of
side
the
of the
point
point
load
load
and
and
find
find
the
the
shear
shear
force
force
diagram
diagram
here,
here,
and
and
then you
then you
can
can
consider
consider
right
right
side.
side.
So
So
the
the
shear
shear
force
force
will
will
change
change very
in a
in a
drastic
drastic
manner,
manner,
in a
in a
discontinuous
discontinuous
manner.
manner.
But
But
for a
for a
bending
bending
moment
moment
case,
case,
the
the
change
change
is
is
either
either
linear,
linear,
which is
which is
proportional
proportional
to
to
x,
x,
or it
or it
could be
could be
non-linear
non-linear
as
as
well.
well.
For
For
the
the
varying
varying
load,
load,
for the
for the
varying
varying
load, it
load, it
could
could
be a
be a
non-linear,
non-linear,
which
which
will
will
be
be
proportional
proportional
to
to
x
x
square
square
or
or
x
x
cube.
cube.
So
So
if you
if you
have
have
a
a
varying
varying
load,
load,
then the
then the
bending
bending
moment
moment
you
you
will
will
get
get
some
some
kx
kx
squared
square
or
or
even
even
higher
higher
kx
kx
cube.
cube.
So it
So
will
it
be
will be
look
look
like
like
this
this
in
in
compared to
compared to
this.
this.
So
So
this is
this is
our
our
present
present
case.
case.
And if
And
you
if
have a
you have a
varying
varying
load,
load,
then
then
it
it
will
will
in
in
blue
blue
color,
color,
which is
which is
proportional
proportional
to
to
x.
x.
And in
And
the
in the
present
present
case,
case,
it
it
is
is
proportional
proportional
to
to
x.
x.
Or
Or
in the
in the
present
present
case, it
case,
is
it is
proportional
proportional
to
to
x,
x,
and
and
for the
for the
varying
varying
load, it
load,
is
it is
proportional
proportional
to
to
x
x
square.
square.
So
So
any
any
doubt?
doubt?
So
So
if you
if you
have
have
a
a
bending
bending
moment
moment
which
which
is
is
proportional to
proportional to
x
x
square,
square
like
like
this.
this,
So this is
this
your
is a
bending
bending
moment
moment
diagram.
diagram,
This
this
is
is
x.
x.
You
You
can
can
also
also
find the
find the
location of
location
the
of the
maximum
maximum
bending
bending
moment.
moment.
So
So
this is
this
the
is the
location
location
where
where
you
you
have a
have a
maximum
maximum
bending
bending
moment,
moment,
and you
and you
can
can
find
find
this
this
xc,
xc,
or
or
let's say
let's say
x
x
naught,
naught,
which
which
is
is
the
the
location
location
where
where
your
your
bending
bending
moment is
moment is
maximum.
maximum.
And you
And
can
you can
see the
see the
slope
slope
here is
here is
0,
zero,
which
which
means
means
the
the
rate
rate
of
of
change
change
of
of
bending
bending
moment
moment
with
with
respect
respect
to
to
x
x
is
is
0,
zero,
because the
because the
slope is
slope is
0
zero
here.
here.
So
So
you
you
need a
need a
bending
bending
moment
moment
expression,
expression,
just
just
like
like
here we
here we
found
found
this
this
bending
bending
moment
moment
expression,
expression,
and you
and you
need to
need to
differentiate it
differentiate it
with
with
x.
x.
For
For
example,
example,
let's say
let's
you
say
have
you
a
have a
bending
bending
moment
moment
expression which
expression which
is
is
kx
kx
plus
plus
x
x
squared.
squared.
You
You
just
just
differentiate
differentiate
it,
it,
and you
and
will
you will
get
get
here
here
k
k
plus
plus
2x
2x
equal to
equal to
0,
0,
and you
and
will
you will
get
get
x
x
minus
minus
k,
k,
and
and
x
x
is
is
minus
minus
k
k
by
by
2.
2.
So
So
this is
this
the
is the
location
location
minus
minus
k
k
by
by
2
2,
where
where
you
you
get
get
this
this
slope
slope
0.
0.
And
And
here
here
you
you
will
will
find the
find the
bending
bending
moment
moment
is
is
maximum.
maximum.
So
So
you
you
can
can
actually
actually
use
use
this
this
concept to
concept to
find the
find the
maximum
maximum
bending
bending
moment,
moment,
but
but
also at
also
the
at the
same
same
time you
time you
need to
need to
take
take
care.
care.
For
For
example,
example,
if you
if you
have
have
a
a
complicated
complicated
system where
system
you
where
have
you
a
have a
multiple
multiple
loads
loads
like
like
this,
this,
and
and
also the
also the
point
point
load.
load,
In
in
that
that
case,
case
what
what
happens? The
happens, the
bending
bending
moment
moment
can
can
have a
have a
different
different
slope
slope
like
like
this.
this.
So
So
you
you
will
will
have a
have a
zero
zero
slope
slope
here,
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 here.
here.
So in
So in
that
that
case, you
case you
need to
need to
take a
take a
caution.
caution.
But in
But in
a
a
simple
simple
systems
systems
where
where
you
you
have
have
a
a
one
one
varying
varying
load,
load,
in
in
that
that
case,
case
the
the
bending
bending
moment will
moment
be
will be
behave
behave
like
like
this
this
one,
one,
which is
which is
proportional
proportional
to
to
x to
x
the
to the
power
power
n,
n,
and
and
n
n
could be 2, 3 or 4 or so on. In that case, you can actually find the location by just calculating the slope or just differentiating the bending moment equation in x, and then calculate the x where it is 0, and that will be the location for the maximum bending moment. If you have only a point load, And the best practice is to calculate the bending moment at each near each lobe and to check where you have a higher bending moment. So until now, any doubt in any question? If not, then we can end this class now. There are a few more problems left, one or two questions left, which is solved using the same concept. So you can try this question, and I will solve this question again in the next class. So only 3 questions left, so you can try yourself how to solve this question. So the next question, for the next question, you need to use these relations here. So by using this relation, you can actually find the bending moment as well as the shear force as a function of x and L. And in the last one, it's a simple question where you need to draw the shear force and bending moment diagram. So basically, there will be a resultant force R. You need to find the normal reaction, and then you have to draw the shear force diagram and the bending moment diagram, which will be applicable to this. So since it's a varying load, here the bending moment will be proportional to x square or x cube. So it will be curve, parabolic curve kind of a profile rather than a straight line. So rather than this, like a straight line, it will be a curve kind of a profile. So try this problem by yourself, and then we will discuss this problem in the next class. Okay, thank you.